My name is Langston Wilcox, and here's my presentation for Lab 2, Lines of Charge. Today I'll be discussing a computational model of two charge tapes exerting an electric force on each other. The purpose of this lab was to estimate the amount of charge on each tape required for one to float above the other. The charge will be distributed evenly in our model. I will also address what assumptions we made and the magnitude of the charge calculated by the model. Here are a few key principles. We have Newton's second law, which explains how an object's motion is influenced by external forces, electric force, which is the force between two charged objects and is crucial to the experiment, electric field of a point charge, which helps us understand how a single charge creates an electric field in space, and lastly, the superposition principle, which helps us sum the electric fields from all charges to find the total effect. Here's a preview of the lab results. For lab 1, the tape charge was 1.26 e to the negative 8 coulombs, the electric force was 1.96 e to the negative 3 newtons, and the gravitational force was 1.96 e to the negative 3 newtons. For lab 2, the tape charge was 2 e to the negative 8 coulombs, the electric force was 4.59 e to the negative 4 newtons, and the gravitational force was 1.96 e to the negative 3 newtons. For the experiment, our system was 8-inch pieces of tape, and the environment was our surroundings. GlowScript was used to model the charges and calculate the electric force, and initially we used a neutral piece of tape and placed it on the table and used two upper tapes that were pressed and ripped off to determine the charge on each tape. Our experiments were based on these assumptions. For lab 1, equal charge on the upper tapes, negligible air resistance, uniform charge distribution, and a centralized point charge for the base tape. For lab 2, the new model and calculations in lab 2 are expected to be more accurate than those from lab 1. Some important observations during the lab 1 experiment include the U-tape was attracted to the hand, indicating an opposite charge. The U-tapes showed minimal attraction to neutral objects, and a strong repulsive force between the two U-tapes confirmed they carried like charges. Here are some of our preliminary experiments from lab 1. And here are our results from our lab 1 experiment. Here's my lab 1 code and model, which shows how the tapes needed to be very close for the top tape to move. Here's some of my lab 2 code, which it takes in the values from lab 1 and recalculates the forces. Here's the rest of my lab 2 code. Here's my lab 2 model, which shows the new calculations. Potential errors in the experiment could arise from bad measurements, incorrect lab 1 calculations or code, and mistakes in value insertion during lab 2 coding. The answer for the what-if question is the point charge is 1.26 e to the negative 8 coulombs, and the line charge is 2 e to the negative 8 coulombs. My answer for the why question is that the point charge model only considered a single atom's charge on the tape, while the line charge model calculated the charge across the entire tape. The line charge value is likely closer to the real charge because it takes the full tape into account rather than just one atom. In conclusion, the computational model helped me estimate the charge required to make one tape float above the other. The line charge model provided a more accurate estimate than the point charge model. We assumed a uniform charge distribution and a centralized point charge for simplicity. And the experiment highlighted the importance of using realistic models to understand electrostatic forces. Thank you.